Hi, how are you? Can everybody hear me?
Yes.
Yes, sir.
Okay, good. All right, great. I can hear you. Okay, how's everybody? I made a little change. I had posted homework assignment number 1 and had said that it was due on this Thursday, 9/2, I guess, but I changed that to next Thursday because I realized that that was just a little bit too soon. We haven't really. I mean, the problems on that homework assignment number 1 are not. They're not terribly difficult, and they're introductory of a kind of an introductory nature, and you should be able to do them, but we haven't talked about that. They're not on what we're talking about right now. I'm talking about something else. I'm introducing Fourier. What I'm doing right now is I'm introducing Fourier series by way of using it to solve an example of a PDE, namely the wave equation. So that's what I did on Thursday. I did sort of part 1 on Thursday, and I'm going to do part 2 today, and we're going to get through that. But the problems on homework assignment number 1 are different. So we'll talk about that a little more like this Thursday or something. But anyway, so I just made that due next week. I'm just trying to it's a timing issue. Okay. So does anybody have any questions about anything? While I get my get sort of organized here. Okay, wait, hang on a second. Wait, just give me a second. I can't find my stylus. I'm going to be in deep trouble here if I can't find the stylus. Hold on. Okay, got it. Rolled onto the floor. All right, so let's see. Any
Professor?
questions? Yes.
Yeah, I have a quick question about office hours. So office hours are on Tuesdays and Thursday, or just one of the days?
Both. Let's see, what did I post on the here? Let me just remind myself what I posted on the website. Wait, hang on a second.
Recording stopped.
Something strange. Something strange is going on here. All right, I'm not going to worry about that right now. I'm okay. The answer to your question is Tuesday. Yeah, Tuesdays and Thursdays. Okay. What did I say on the website? Did I say before class or after class? That's what I'm having trouble remembering. I don't want to contradict.
It was, we discussed last after class.
After class, yeah. Okay, right. So, let's see, office hour. Yeah. So, wait, hang on a second. Oh no, I've got no. I'm sorry. That's a typo. Yeah, I'm sorry. I have to fix that. That's a typo. It says Tuesday, Thursday, 6 to 7, but that's not really. You know what? Let me think about that because I'm sorry. I just realized that that's a typo, and I actually want to think about that a little bit more because now that I think about it, I think that what might work better is something like an hour after class on Tuesday and an hour before class on Thursday. That's sort of what. So Thursday would be like 3 to 4, and Tuesday would be, 5:30 to 6:30. So let me think about that and get back to you on that. I'm sorry, I didn't get that. I didn't get that completely nailed down. Okay, all right. Anything else before we get started? Any other questions about anything?
Yeah, Professor, can you hear me?
Yes.
Yes,
I can.
It said you stopped recording. So if you want to record the lecture, I'm not sure if that's an accident or on purpose.
I did stop recording, and I want to resume it as soon as I start. As soon as we start
cool.
about the math.
I just wasn't sure if that's an accident or not.
Okay, all right. Is that it? Was that your question about the recording?
Yeah. I wasn't sure if it was an accident or not, so I just wanted to draw your attention to it, just to be safe.
Yeah, no, I didn't want to record my fumbling around trying to find the website. Okay.
Recording in progress.
So I'm recording again, and let me share the screen here, and I'll start the whiteboard, and I'll just remind you what we're doing. So I thought, the way we would start out was just by going through an example of a boundary value problem, what's called a boundary value problem, and looking at how to solve it, and using that as a way of introducing the concept of Fourier series. So as soon as I see. This is. Okay, there is really something strange going on with my computer. But you can see me and hear me fine, can't you? Yes. Yeah, okay. All right.
Yes.
All right. Okay, well, never mind then. All right. Can everybody see the
whiteboard?
The whiteboard.
Yes.
Yes. Okay, good. All right. So let me just remind you of this problem. We have an axis like so, and here's 0, and here's some number L, which is the length, stands for the length, and we have a string, and the string is stretching from this point to this point, and it's under tension. So if it's not moving at all, it's just going to go straight from 0 to L. But we sort of pull the string or stretch it or something, so it starts out in some initial configuration. So f of x is some function on the interval from 0 to L, which describes the initial position. And then we let go, and the string vibrates. Okay, so we'll let u of xt be, so we're going to have the u axis is going to be this vertical axis here, And so u of xt is going to be the height at time t and position x. And because the string is tied down at the ends, u of 0t and u of lt, these are represent the two endpoints. These are 0 for all t. And since f of x is the initial position, f of x is just u of x at time 0. All right, and we'll just assume that the initial velocity, just to keep it simple to start out with, let's just assume that the initial velocity is 0. All right, so this vibrating string will satisfy the following partial differential equation. The second partial of u with respect to t squared is some constant squared times the second partial of u with respect to x squared. All right, this is called the wave equation, the one-dimensional wave equation. C is a constant that depends on physical parameters of the string. All right, now.
Sorry, I don't mean to interrupt you. There's
okay.
Some people waiting in the waiting room.
Oh, I thought okay. All right. Thanks for pointing that out. I thought I disabled the waiting room. Let's see.
Never mind. It looks like they're actually in your personal room, not in the class or the class Zoom. We're directing them to the right place.
Oh, I see. So they just went to my Zoom personal room instead of following the link to the class. Oh, okay. Yeah. All right. Yes. If you could please just send them a message or something. Anybody like that, anybody in that situation, send them a message and send them the link. Okay. Yeah. Thanks. All right. Thanks. I appreciate that. Okay. All right. Yeah. I believe that the waiting room is disabled now. So anybody that comes along should just be able to come in. Okay. So, all right. So here's the wave equation. And then last time what we did was we produced a solution. Okay. And the solution that we came up with, well, if you pick an n.
I don't think we could see your whiteboard.
All right, because I stopped sharing, right? Yeah, okay. Sorry. Okay. All right, how about now?
We're good now.
Yeah, okay, all right. So last time we came up with a solution. If you pick an n, a positive integer, then for each n, there's a solution. And the solution is given by you call it u sub n xt, and it's the cosine of n pi c t over L times the sine of n pi x over L. So you can just take the partial derivatives of this function and plug them into the equation and see that it satisfies the equation. All right. Now, because the equation is linear, if I take any sum of these two or any constant times any of these, that's also going to be a solution. So in fact, we get this very general solution, which is gotten by just taking a linear combination of all of them. Now, I'm going to call the coefficients b sub n. Last time I called them a sub n, but I'm gonna call them b sub n now, just because that's a little more consistent with what's in the book. So we have b sub n times the cosine. Let me abbreviate this constant to lambda n. So we have the cosine of lambda nt times the sine of n pi x over L, where lambda n is n pi c over L. That's the coefficient that we had here. All right, so here's a linear combination of the u sub n's, which is also a solution. And notice, by the way, that we're taking an infinite linear combination. So that was one of the inspired ideas of Fourier, is that we could consider infinite linear combinations of solutions to get a solution. And he had no justification for that. He didn't have any particular proof that such a linear combination would even converge, or that you could take the derivative of an infinite sum like this and you would get the infinite sums of derivatives, thereby verifying that it really is a solution. In fact, not only did he not have rigorous proofs of those facts, but in Fourier's day, they didn't even have rigorous definitions of those notions. So mathematicians didn't even have a definition of what it meant for an infinite sum to converge. The whole concept of a formal definition of convergence using epsilons and deltas and things of that sort didn't even come about until much later, and was due to Cauchy and other people. In fact, it was work like Fourier's work that motivated people to try to figure out what those things meant, because nobody really had the slightest idea. So when Fourier said, oh yeah, let's take an infinite linear combination of solutions and that'll also be a solution, nobody could really prove them right or wrong, because they didn't even have definitions to use to make the proofs. Okay, so we're just gonna follow that and just wing it and not worry about that. We'll get into that. We'll get into that theory a little bit more later as we go along. Okay, so u of x is a kind of general solution. Oh, and Fourier went one step further and he said all the solutions look like this. So that's even harder to prove. But again, let's not worry about that. Okay, so how do we find the coefficients b sub n? In order to get a particular solution to our particular problem, we need to then find the values of the coefficients b sub n, and then we're done. Well, the way we do that is by using the initial condition. So if you set t equal to 0 and plug that in, then you get u of x0, which is our initial position, f of x. And when I plug that into here, when t is 0, the cosine of 0 is 1. And so I just get the sum as n goes from 1 to infinity of b sub n times the sine of n pi x over L. So if we could express the function f as a linear combination of these sine functions, then those coefficients in that linear combination are going to be the coefficients that we'll put into the solution of our PDE. So the idea is to express a given function f as a linear combination like this. So we can do that, and this is called the Fourier sine series. If you use cosines instead of sines, then that's called the Fourier cosine series. And for a general function, there will be a Fourier series that'll have sines and cosines in it. This is we're going to look at odd functions, so we'll be interested in the Fourier sine series. Okay, so let's depart now a little bit from this PDE problem and look at the whole idea of a Fourier series. Does anybody have any questions about this at this point? Okay, so the procedure at this point is going to be to use the specific function f of x, which is the initial condition, and use that function to obtain the values of these coefficients. And once we put those numbers in, we're going to have an explicit solution to our problem, which depends on the initial condition. How the string vibrates through time depends on the initial position it was in when you first let it go. All right, so that's the idea. So what we want to do is generalize a little bit and just consider f of x to be an odd 2L periodic function. This will be our sort of general setup here. Okay, so an odd function, recall that an odd function means that f of minus x is minus f of x. So examples of odd functions are things like, well, the sine of x is an odd function. Let's see, x cubed is an odd function. F of x equals x squared is not odd. That's actually an example of an even function. We'll talk about even functions later. But anyway, so let's suppose that f is an odd function, and let's say it's 2L periodic. Now, a function, I'll make a little definition here. A function, I'll call it, say, g of x, is called periodic with period t if g of x plus t is equal to g of x for all x. That's what it means to be periodic with period t. So you know examples of periodic functions. The trig functions are periodic. So sine of x, for example, is equal to sine of x plus 2 pi for all x. Same thing with the cosine. The cosine of x is the cosine of x plus 2 pi. So, so sine and cosine are 2 pi periodic. You know, in other words, you know, if you look at the graph, you know, just to put it into words, you know, you look at the graph and it does this. Let's say this is 0 and this is 2 pi. And then it just repeats after that. Every two pi, the picture just repeats. All right. And so what that means is you could take any interval of length 2 pi. It doesn't have to be 0 to 2 pi. You could go from, let's say, pi to 3 pi. And on any interval of length 2 pi, that tells you the whole story, right? Everything you need to know about the function is determined by what it does on any interval of length 2 pi, if it's 2 pi periodic. All right, now the period isn't necessarily unique. If let's say f of x is T periodic, so it's periodic with period P, T, excuse me, then it's also automatically 2T periodic or 3T periodic, right? So if I take any multiple, any integer multiple, positive integer multiple of the period, that's also going to be another period. So like the sine of x is, the sine function is 2 pi periodic. It's also 4 pi periodic or 6 pi periodic. Now you could ask, given a periodic function, what's the minimal period? What's the smallest period it has? And then you could call that the period or the fundamental period or whatever. We're not really going to be concerned with that right now. The main thing is we just want to know what it means for a function to be periodic. Okay, so f is going to be an odd function that's 2L periodic. Okay, so f is odd with period 2L. Okay, now let's suppose that f has a Fourier sine series, and that furthermore f is equal to its Fourier sine series. Just suppose that f is given by an expression of this form. Okay. Oh, and by the way, the reason I'm looking at odd functions is because we're looking at this Fourier sine series. So if I go back, okay, so going back to the beginning, here's the wave equation problem we're trying to solve. Here's the boundary value problem we're trying to solve. We came up with this solution. We plugged in t equals 0, and we got this formula right here for the initial position, and it's a sum of sine functions. So that's why we're looking at Fourier sine series or sums of sine functions, because that's what you get for the initial position in this problem. But notice the sine function's odd. So any linear combination of sine functions like this is going to be odd. So f would have to be an odd function if we expanded it to, let's say, the entire real line, say going from, minus L to plus L, or, so f has got to be an odd function if it's going to be a sum of odd functions like this. So that's why we're looking at odd functions. Okay, so we have this function f, and let's suppose that it's expressed like this. Then how could we figure out the coefficients? That's the question. Well, what we can do is we can use the following orthogonality formula. The sine function, these sine n pi x over L functions for different values of n satisfy an orthogonality condition, which I will now write down. So this is the basis for using these as the terms in a Fourier series. The sine of n pi x over L times the, let me get the right thing here. If I take the sine of n pi x over L times the sine of m pi x over L, n and m are two integers, and then I integrate that from minus L to L, then what do I get? Well, if n and m are different, I'll just get 0. And if n and m are the same, then I'll just get L. All right, so that's the orthogonality condition for the sine function. And we'll
Could you?
prove this in a second. Yes, go ahead, question.
Oh yeah, I was just gonna ask you if you could do a brief explanation of how that proves orthogonality.
Or you why this orthogonality formula is true?
Yeah.
Yeah. Well, actually, yeah. Let's just do it now. I was going to illustrate a use of it and then do it, but let's just do it first, and then we'll give the use of it. Okay. So here's the way to prove it. It's just a calculation. All right. So it's just a simple calculation. So let's go through it. It's basic to this whole subject. So okay. So how do you check this? Okay. So proof of orthogonality. I don't want it to be a big mystery. Okay, so we have two relevant trig identities that we're going to use. These are the angle sum identities. The cosine of alpha plus beta is the cosine of alpha cosine of beta minus sine alpha sine beta. I'm sure you've seen these before. You maybe don't have them memorized. That's all right. I always have trouble remembering these things. I always sort of remember sort of what they look like, but with all the plus signs and the minus signs and whatnot, it's hard to sort of keep them all straight. You can always just look them up. They're easy to look up. Okay, so we have these two identities, and if we put them together, if we subtract the first one from the second one, then we get that the cosine of alpha minus beta minus the cosine of alpha plus beta is equal to, then these terms, the first two terms cancel, and then we just get twice the sine of alpha sine of beta. All right, so we can use this now to integrate this product. We have sine of n pi x over L times sine of m pi x over L dx from minus L to L. Let's assume that n and m are different. Okay, so then this is going to be, so according to this identity right here, this is going to be 1/2, bring the 1/2 over to the other side, the integral of minus L to L of cosine alpha minus beta, so that'll be n minus m times pi x over L, minus the integral from minus L to L of cosine n plus m pi x over L. This is dx. Now, if you just do these integrals, you'll get 1/2. So what's the integral? It's the integral. So the integral of the cosine is the sine. So you'll have the sine of n minus m pi x over L. This is going from minus L to L. And then, you have to divide by the coefficient. Now here's where I'm using that n is not equal to m. Okay, because n is not equal to m, n minus m is non-zero, and so I can divide by it. So I get L over n minus m pi out here, and that's the first term. And then the other term is L over n minus m pi. And then I have the sine of n plus m pi x over L, also from minus L to L. Okay, so now if I plug in L for x, that will cancel with the L on the bottom, and I'll have the sine of n minus m pi, which is 0, because the sine of an integer times pi is just 0, right? The sine of any integer times pi is 0. Say k is an integer. All right, and similarly for the second term, the sine of n plus m pi x over L is 0. All right, so that's how we get 0 when n is not equal to m.
So did we just sort of assume that the integral of these two vectors is an inner product, or?
No, I'm not. Well, first of all, no, I'm not assuming. I'm not assuming anything. I'm not assuming. We're just doing a computation. That's all.
Okay.
Just doing a computation. I mean, if you think of these functions as vectors, and you define an inner product to be the integral of the product of the functions, then we are saying that the inner product of these two functions is 0. So yeah, these things are forming an orthonormal set of vectors in the vector space of continuous functions. So yeah, we are proving that it's an orthonormal or an orthogonal set. But we're not assuming that. We're just checking it. We're just computing. So I'm just
I got you.
Yeah, you just use a trig identity. Use these trig identities for the cosine of the sum and difference of two angles to convert this thing into this integral and evaluate the integral. And when n is not equal to m, you get 0. And then when n is equal to m, that's a little different. Now we're going to get the integral from minus L to L of the sine of n pi x over L squared, right? Because n is equal to m. And so now for this, we just use this other trig identity. It's a half angle identity for the sine squared. So the sine squared is equal to 1/2 times 1 minus the cosine of 2 n pi x over L. And this goes from minus L to L. And so you work this out. And what do you get? You get, well, the second term, the integral of the cosine is going to be the sine times a constant. And then when you evaluate that between minus L and L, you just get 0 at the endpoints. So you really only have the first term. So that's 1/2 times 2L, which comes out to L. So this integral is easy and it just comes out to L. All right, so that's how you get.
What happens to the n in that case?
The n.
Where did the
well, I left it out. Okay, I'm sorry, it was a typo. I have the sine of n pi x over L squared. So that's 1/2 times the quantity 1 minus the cosine of 2 n pi x over L. Sorry, I left it out. That's a typo. But nevertheless, when you integrate the second term, the integral of the cosine of 2 n pi x over L is going to be the sine of 2 n pi x over L times a constant.
Right.
So if I plug in L, I get the sine of 2 n pi, which is 0.
Okay, thank you.
If I plug in minus L, I get the sine of 2 n pi is 0. So it goes. So the n goes away ultimately at the end. All right. So you get okay. So these are the So you need to remember these formulas. These are important. We're going to use these all the time. This is the orthogonality conditions for the sine function. Oh, and there are also orthogonality conditions for the cosine function, and the sine and the cosine mixed. But we're not using those today. So they're similar, but we're not using them right now. So we'll do that later. Okay, so what's the point of the orthogonality conditions? Well, the orthogonality conditions enable us to find the coefficients of the Fourier sine series. So let me just show you how that goes. It's pretty straightforward. All right, so remember, we're supposing that f of x is equal to a sum of sine functions with coefficients like this, and goes from 1 to infinity. So here's what we're going to do. We're going to take f of x times the sine of m pi x over L. So the way I want to think about this is fix an m. So pick an m and fix it. And then n varies, because n is our n is the index of the summation. So n is a variable which is going all the way from 1 to infinity. Now just fix an m. Okay, so if I multiply f of x times sine m pi x over L and integrate from minus L to L, what do I get? Well, let me substitute in the formula for f of x. F of x is supposedly the sum, as n goes from 1 to infinity, of bn sine n pi x over L. And then we're multiplying that by sine of m pi x over L and integrating. Okay, well, now we're back in Fourier's day, when we don't worry about things like, do infinite sums converge? Can you interchange an integral with an infinite sum? Those sorts of rigorous questions don't concern us at the moment. All right, so I can pass the integral into the sum and get the sum as n goes to infinity of b sub n times the integral from minus L to L of the sine of n pi x over L times the sine of m pi x over L. All right, well, we just got through evaluating this integral. And what we discovered was that if n and m are different, then the integral is 0. So that means that we're going to get 0 for every single term in this entire expression, except for the one where the index is equal to m. And in the one case where the index is equal to m, we're just going to get b sub m times what the integral of that product comes out to, which is L. So b sub m times L is equal to this expression right there. So if I divide both sides by L, I've solved for b sub m. So b sub m is equal to 1 over L times the integral from minus L to L of f of x times the sine of m pi x over L. Now, the n is gone. N is no longer being used, so that variable is now free to use again. So if we want, we can just write this same formula, but just use an n instead of an m. I only introduced m for purposes of multiplying and integrating and getting the answer to come out. But at the end of the day, we could just write b sub n, the nth coefficient is given by this formula. Now, before we move on from this, let me just point out if f of x, well, I shouldn't say if, I should say since. So if f of x is given by a linear combination of sine functions, then f of x would have to be an odd function. So this formula doesn't make any sense unless f is an odd function. So I'm not going to say if f is odd. I'm going to say since f is odd, since f is odd, f of x times sine of n pi x over L is even, right? Because the sine of n pi x over L is odd. So since f is odd and the sine of n pi x over L is odd, the product of two odd functions is even. An odd function times an odd function is an even function. And so this integrand right here is even. So instead of integrating from minus L to L, why don't we just simplify things a little bit and integrate from 0 to L and double it? Just use symmetry, right? And if you integrate an odd function from minus L to L, I'm sorry, if you integrate an even function from minus L to L, that's the same thing as just integrating from 0 to L and doubling it. Okay, so here's the formula that we end up with for the Fourier coefficient. All right, so that's it. So this is the formula that you get for the nth Fourier coefficient of an odd 2L periodic function. And so using this formula, we can compute b sub n. We'll do an example eventually. Okay, all right, does anybody have any questions about that? Any questions at all? All right, well, let's go back. Yes.
So the only constraint there is that your f of x, which is what the string looks like initially, is that it has to be I think it was an odd function. Is it right? Because so you have this answer for any b sub n, but I just want to remember that you still have a constraint there, right?
Yeah. Well, okay. So right. So I pulled a little. Yeah. So I pulled a little fast one on you. When we started out, we were talking about a function on the positive interval from 0 to L, right? There is no negative x being considered here. We have this string stretched between 0 and L. And then we got a formula for the solution, and the coefficients were given by this Fourier sine series. So we want to find the coefficients of this expression for f. Okay, so in order to determine a formula for the coefficients of the Fourier sine series, I started talking about 2L periodic functions defined on, the whole real line. And I needed to integrate from minus L to L to get the orthogonality formula and to get the coefficients. But in our original problem, we only had f going from 0 to L. So there's a little bit of a confusion there. I started with something that only went from 0 to L, and now I need something that goes from minus L to L. So I think that's, is that related to your question? Is that kind of what you're asking about?
Yes, I gotcha.
Yeah. Okay. So so continuing with that question, with that point, let's go back to the problem now. Let's go back to the wave equation, and see how we deal with that. Okay. So let's go back to our original problem. F of x is defined on 0 to L, right? So it's this function that looks, like, well, whatever it looks like, here's L, and it's something, like this. Okay, so what we need to do to carry out to implement our Fourier sine series business that we just did, we need to extend the F to a odd 2L periodic function, defined on all of R. So how do you do that? Let me just, okay, well, I'm just going to try to draw the picture a little more neatly. All right, so okay, so here's the interval from 0 to L, and let's say my function goes like this. All right, then what I'm going to do is I'm going to go to minus L back here, and I'm just going to, flip it around, just rotate around 180 degrees to get the graph over on the other side. So it's going to go like this, like that. And now I have an odd function. And then what I do is I just repeat it to make it periodic, I just repeat it every 2L. Although I don't really I don't really care about anything beyond minus L to L for purposes of this problem. But if I wanted to continue it on, I could then just continue it, etc. So I'm going to end up with a function that is 2n periodic on the entire real line, and is odd. So this is called the odd periodic extension of F. Okay, I start with an arbitrary function on the interval from 0 to L, and then I extend it to a function defined on the entire real line, which is odd and 2L periodic. And then this whole discussion that I just went through a little bit ago about the Fourier sine series of a 2L periodic odd function, we can now apply that to this extension, this odd periodic extension of our original function F. And then if the formula for this Fourier sine series gives you the values of F everywhere on the real line, then in particular, if I just restrict to 0L, I'm going to get the values of F on the interval from 0 to L, which is all we really cared about to begin with for the purposes of the boundary value problem. The way, applying the wave equation to this string, we only really care about what happens from 0 to L. Okay, but I have to sort of extend it out to the interval from minus L to L in order to make sense of the Fourier coefficients. Okay, so does that make sense? I hope that's clear. Is that there was a little
Thank you.
little switcheroo going on there in order to make this work. Okay, so now we can write down the final solution, the final solution to our problem. So the final solution, we get the final particular solution to our original boundary value problem is, so these by our boundary, the boundary value, I'm talking about the original problem that we started out asking about, was a string stretched from 0 to L with initial position f of x. We let it vibrate. And what is the equation of motion? What's the function that describes the equation of motion? And so here we go. It's u of x t equals the sum as n goes from 1 to infinity of b sub n times cosine lambda sub n t times sine of n pi x over L, where lambda n is equal to n pi c over L. And the b sub n's are gotten by just computing the coefficients of the Fourier sine series of the initial position. F of x is the where f of x is the initial position. Okay, so that's it. So we've solved the boundary value problem that we started out with. This was Fourier's method. He came up with this whole business. In the process of doing it, he made a number of radical assertions. Not mainly that by taking an infinite sum of these functions, you still get a solution, and that every solution has that form. So in particular, he's saying that every function can be expressed as an infinite sum of trig functions like this. None of these things are obviously true, but they are true under various hypotheses. And so that is an introduction to Fourier series as it applies to PDEs. Okay, does anybody have any questions about that? Okay, let's see. Let me look at the chat. Nope. Okay, nope. All right. Okay, great. All right. So we have a few minutes left. So now what I want to do is I want to do an example. Okay. Nothing. We should never do anything without an example. This is something I've learned gradually over the years, is that any sort of mathematical discussion, any talk about a theorem, anything that you do really has to have an example. Because if you can't work out an example, then what good is it, right? Or if you can't think of an example, then what's the point? All right, so I'm going to start an example, but we're not going to have time to finish it. We're going to finish the example on Thursday, but I don't want to waste the remaining time. I just want to get the example started and get it set up, and then we'll just finish it on Thursday. Okay, so let's look at an example. All right, let's actually work out an example. Okay, and these examples are fun and they're interesting to ponder. Okay, so let's say that you took this guitar string, going from 0 to L, and let's just say you did the simplest thing you could sort of think of. You grab the guitar string and you pick it up in the center. You know, you grab it in the middle and you pick it up and pull it taut like that, so that it forms a triangle. Okay, you're holding it pinched between your fingers at the center point, and then you just let go, and then it starts vibrating. Okay, according to some motion, it's going to vibrate back and forth. Okay, so let's write down the solution. Let's solve this problem. Okay, so what is f of x here? So f of x is this triangle wave. We call this a triangle wave. Okay, so f of x is a triangle wave. It's not differentiable because it comes to a point, like the absolute value function, for example, but it is continuous. Okay. All right, so here's the vertical axis here, and let's pick it up to a height of L over 2. So f of x is equal to, so on the interval from 0 to L over 2, this just goes up with a slope of 1. The halfway point is L over 2, and it goes up to L over 2. So it's just x. And then on the interval from L, this is supposed to be an L over 2 up to L, it's just this line going down, which you can compute very easily. It's a line going down with slope minus x, but it has intercept. The y-intercept is up here at L, so it's L minus x. Okay, so that's the formula for the initial position. And then we need the odd periodic extension, right? So in order to compute the Fourier coefficients, which are what we need for our solution, we need the odd periodic extension. So the odd periodic extension, I'm going to try to draw a picture of this. The odd periodic extension is going to look like this. Here's L, and here's L over 2. So it goes up there and down there. Okay, but then we want to extend this in both directions. So here's minus L over 2, here's plus L over 2, and down here, this is going to be minus L over 2, and so it's going to go down to there, and then it's going to turn around and come back up to there. All right, so then if we just keep on going, let's say here's 2L, here's 3L over 2, it's going to go down to there and up to there and so on. It's just going to keep on going up and down. All right, so this is the odd 2L periodic extension of this triangle function. And like I said, this is called a triangle wave. It's kind of like a sine wave, right? It looks it's similar to the sine of pi x over L, except that instead of being smooth and harmonic, it's triangles. All right, so that's the odd periodic extension, and then let's see, we have a couple minutes left. So we need to write down the Fourier coefficients. So these are going to be 2 over L times the integral from 0 to L of f of x times sine n pi x over L dx. So this is going to be 2 over L times, now what's the formula for this function? It's if you look from 0 to L over 2, it's just x. Okay, so we're just going to have the integral from 0 up to L over 2 of x times sine n pi x over L dx. And then, let's see, 2 over L applies to the entire thing. And then we're going to have the integral from L over 2 to L of L minus x times sine n pi x over L dx. Okay, so one last thing, it's 2 over L. The first integral goes from 0 to L over 2, x sine n pi x over L dx. And then the second integral, I'm going to split it up. There's L times the integral from L over 2 to L of sine n pi x over L dx. And then the third term is going to be minus the integral from L over 2 to L of x times sine n pi x over 2 dx. All right, so this is the formula. This is what you get when you go to compute the nth Fourier coefficient for this triangle wave. And so all we need to do now is compute these 3 integrals. So let's call that integral 1, integral 2, and integral 3. And so our next task is going to be to just compute these. And we're going to use integration by parts. So between now and Thursday, I want you to review integration by parts and make sure that you remember how that goes. We're going to use it all the time in this class, okay? We're going to use integration by parts all the time. So you want to review it and just make sure that you are completely proficient at it, and you can just do it without even thinking about it, because it's really, it's hard to kind of overstate how useful integration by parts is and how often it comes up in this sort of thing. Okay, so that's it. I guess we'll stop there. And let's see, does anybody have any questions about anything? Any questions at all? Okay, does this make sense? I mean, does this seem like a reasonable strategy? I mean, we've in the short amount of time, we've only been at this for 2 class periods, and in the short amount of time that we've been at this, we've actually already tackled a really deep problem. I mean, we're figuring out an explicit formula for the equation of motion of something as complicated as a vibrating guitar string. So
yeah, we
really
kind of covered this. We kind of like I don't know about anybody else, but this was like the very, very last few weeks or couple of class periods in my ODE class. We started covering this kind of stuff. So I'm still on pretty solid ground.
Oh, okay. Yeah. When I teach the ODE class, I don't get into this because I spend the whole semester. There's so much to talk about with ODEs that I just don't even bother trying to do this. But yeah, this is, I think the first time I took an undergraduate ODE class, I think we probably started this at the very end. Yeah, kind of, introduce the idea. So, but we're going to go into it in a great amount of depth. Oh, and also, I should just mention, since you brought up ODEs, I should just mention that you do need to go back and kind of look at the material from your ODE class and make sure you recall how all that goes, because we're going to be using that. We're going to be relying on that pretty heavily.
Are there any specific chapters and techniques that you suggest?
Yeah, well, yeah. I was just going to say, yeah. So the main things. So let me just tell you, the main things from the ODE material that we're going to be using are the solutions of second order linear ODEs. So that's a basic topic that you presumably spent a lot of time on, so a second order linear ODE, that's the equation that describes, for example, a mass on a spring, right? If you have a mass hanging from a spring and you pull it down and let it go and it bobs up and down, you get a second order linear ODE, or a swinging pendulum, or something like that. So make sure you review that and you remember how that goes. The solution is typically some kind of harmonic motion, right? So there's that, and then the other thing is you need to review the series solutions, because so the series solutions method, that's where you take an ODE and you assume that your solution is given by a power series. You assume the solution can be represented by a power series. So you plug the power series into the equation and you get some recursive set of equations for the coefficients, and then you use that to solve for the coefficients, and that gives you your solution to the ODE. And we're going to be using that, and we're going to be using it in the case of singular points. And when we do it with singular points, the solutions are going to involve functions like Bessel functions. So I don't know if you got that far in your ODE class. I don't. Some ODE instructors do the singular case and introduce Bessel functions, and some don't. I'll go through it. I mean, I'll develop it all kind of, from scratch in case you haven't seen it before. But we're going to be doing a lot of stuff with Bessel functions and Legendre polynomials and Legendre functions, and So those are the two things, the main thing: second order linear ODEs and series solution method for solving them. That's what you should review. Okay, all right. Anything else? Okay, all right. Well, keep on working on the problems from homework assignment number 1, even though they had nothing to do with what we're talking about. And I'll assign a new batch of problems that will have something to do with what we're talking about. And we're going to meet again on Thursday. And then I guess we don't have class on Tuesday because there's no college. So after this Thursday, we won't see each other again for another week. Okay. All right. So
wait, sorry, did you just say you're assigning a new set of, did you just say you're assigning a new set of problems?
I'm going to be posting assignment number 2 before assignment number 1 is due.
Okay, I got you.
Okay, so I don't know exactly when assignment number 2 is going to be. I don't know the exact due date yet. I haven't really decided that, but you've got 9 days until assignment number 1 is due, and sometime before those 9 days are up, I will be posting assignment number 2. That's all I was saying.
They wouldn't be due at the same time,
though. Well,
yes, they might.
I can't actually rule that out, because if I might actually throw together a couple of Fourier series related problems and call that assignment number 2 and put that up by, let's say, this Thursday or something, and maybe just make that due next Thursday also. So yeah, I can't really rule that out.
But my other question is that some of the homework problems have like a little computer icon next to them. Do you want us to do something different for those? Like, for instance, one of them is like plot a certain graph and it has a computer icon.
Is that true? Is that true on some of the ones I assigned already on assignment number 1?
Yes.
Yes.
Oh, okay. Oh, all right. Okay. Sorry. Okay. Sorry. I didn't really think that. Okay. So on the problems that have a little computer icon and ask you to graph something or plot something, just do that, but don't turn that part in.
Okay.
Just find, I mean, I think I mentioned already, we're going to be using Mathematica. So if you haven't gotten a Mathematica, I believe you just I think you just contact ICIT to get Mathematica. Go to the student help desk and tell them you need Mathematica. I don't think it's more complicated than that, but let me know if you have any problems. But once you have Mathematica on your computer, then if you do have a little icon on a problem that asks you, to plot the solution or something like that, just start playing around with Mathematica and doing it there. I mean, Mathematica is not the only game in town, by the way. I happen to like there's a whatever. There's a lot of software out there for solving math equations and plotting things, but let's just start getting into the habit of using Mathematica, because that's probably the most powerful thing, and that's what we're going to sort of standardize in this class. So do that, but don't worry about turning that part in. If it's graphical or computer based or whatever, don't for now don't worry about turning that in. Okay, all right. Okay, anything else? Anything else? Okay. All right, good. Okay, so keep studying, have a good weekend, or no, don't have a good weekend. Well, yes, have a good weekend, but I'll see you before that happens. I'll see you on Thursday. Okay, all right, bye.
See you.